Okay, Organic Chemistry 2341. We're going to continue on with Chapter 8, which is reactions of alkenes and alkynes. Last chapter, we learned how to make alkenes and alkynes through elimination reactions. Now we're going to learn how that reactivity of that double bond can help us do addition reactions across them. So the first thing we need to think about in our addition reactions here is that pi cloud gives us extra reactivity. Those pi bonds are more reactive than sigma bonds, and therefore they want to react. And so when we react that pi bond and break it up, we end up getting two new sigma bonds formed. Okay, so alkenes are electron rich, and the electron density of that pi bond is above and below that trigonal planar plane created by the sp2 hybridized carbons. Okay, so they typically act as nucleophiles, meaning they are electron rich, and so they act as nucleophiles with things that are electrophilic, that want to have that electron density. Also, simple alkenes do not react with nucleophiles or base reagents that are themselves electron rich. So think about it, if it's already got a lot of electrons, there's no reason for it to react with that electron rich pi cloud. Okay, so the first thing we need to think about when we have these reactions is that because this is a flat trigonal planar molecule, when we start, we can add the two sigma bonds in two different ways. The first one is Syn addition, where we can have both of those new sigma bonds attach at the same side of that double bond, or we can have what we call anti addition, where one sigma bond is created on above the plane and one sigma bond is created below the plane. So because those are two different ways to do it, they actually typically have a different mechanism in it. So if we want to think about what that might look like, let's move up here. So on the bottom here, we show you that if we had one half of a molecule, the yellow sphere, adds at the top, we can have it add Syn, where the green sphere also adds at the top, or we can have it add anti, where the green sphere adds at the bottom here. Okay. So on the next slide, here's a series of the different reactions. We're going to go through this chapter, but I wanted to signify it with this cyclohexene. The reason I want to start with the cyclohexene as an example is it helps us determine whether we have Syn or anti configuration, because we don't have that free rotation available after we do that, after we break that double bond. So this is going to help us kind of overall get the idea of whether we get Syn or anti addition on all the different reactions we have. And we have a variety of reactions we're going to learn in this chapter and the next. Everything from the making diols to adding acids across it, adding water across the double bond, adding two halogens across the double bond, a halogen and an OH across the double bond, and just hydration as well. And we can also end up not only doing that, but we can reduce this down and get rid of the, so we can add hydrogen across that double bond to get rid of the alkene altogether, or we can even oxidize that down to break it up into a couple of carbonyl-like compounds. Okay, so let's start with the first one that we're gonna have, and it's the hydrohalogenation. Now, in that slide before, it said we can have a Syn addition or an anti addition. All depends on the type of reaction we are going through. Okay, so in the hydrohalogenation, we typically have two successive Lewis acid-base reactions. The first reaction is where the alkene is acting as a nucleophile and starts to interact with the partially positive hydrogen on the HBr. And then when that happens, it forms that new sigma bond, generating our carbocation here. The carbocation here then acts as an electrophile and attacks the bromine, okay? Or it's a nucleophilic attack by the bromine onto the carbocation to form our second sigma bond, okay? So because of our intermediate here, our carbocation is also a trigonal planar, a hybridized carbon. That means that this bromine can either go to the top here or to the bottom here, which means we can get Syn or anti configuration. In fact, we get a 50-50 mixture of Syn addition because it comes at the top, and a 50-50 mixture of the anti because it comes from the bottom half of the time. Okay, so what does the energy diagram look like this? Well, because we're forming a carbocation, that means we're forming an intermediate. So we're going to have this intermediate hump in here where the carbocation is formed. So the first activation energy hump is that formation of the bond, the sigma bond with the hydrogen here, going through the transition state where we're starting to form this hydrogen bond, and we're starting to use those electrons from the double bond to form that bond with the hydrogen and give us our true carbocation here intermediate. Then the second interaction is when the carbocation is being interacted with by the bromine and starts to form that next sigma bond. That's that second activation energy before we cascade down into products, okay? So because we're forming that carbocation, we have this two-step reaction diagram where we have the formation of that carbocation intermediate. Okay, so think anytime you form a carbocation, you have a possibility of Syn or Anti Addition. Okay, now how do we know which side it's going to go on? Which side the hydrogen is going to go on first? Okay, so we have a rule for this, and it's called Markovna rule. So in an unsymmetrical alkene, the acid is going to add across the double bond, giving a specific product, okay? And the rule says that the electrophile, usually in this case the hydrogen, if we're adding an HCl or HBr across it, ends up on the sp2 hybridized carbon with the greatest number of hydrogens. So what you can say is that if you have one hydrogen on one side here versus two hydrogens on this side, the hydrogen is going to go on the side that already has two hydrogens on it, okay? And there's a couple of reasons for this, but we want to make sure we understand this rule first. So if you can remember that if it already has a lot of hydrogens, it's going to get the hydrogen, okay? And that's because we form the most stable carbocation. Okay, let's look at that. Okay, so because we want to add the hydrogen to the least substituted carbon, or the one with the most hydrogens on it, that means the carbocation is going to be on the more substituted carbon or the more stable carbocation. So let's look at the addition of HBr across this propene right here. So we have a choice. We can put the hydrogen on this side, or we can put the hydrogen on this side. So if we put the hydrogen on this center carbon right here, what we're going to end up doing is forming a primary carbocation, okay? And to form that primary carbocation, that's the least stable carbocation that we can form in this reaction. Therefore, it is not going to happen, okay? So instead, if we add the hydrogen to this terminal carbon right here, that gives us a secondary carbocation. That secondary carbocation is more stable and easier to form, and therefore it is the main product from the reaction. That doesn't mean this doesn't happen. It happens in very small amounts. You always think about forming the more stable carbocation first, if at all possible, and then it reacts to form it. So if we look at our energy diagram here, to form the primary carbocation, it's a much higher activation energy, and the energy of that carbocation is much higher, okay? So what we'll need to do is hopefully have it form in the, oh no. Okay, so in the first energy diagram here, to form that primary carbocation, it takes a lot higher activation energy, and that product is a lot higher in energy. In the case of forming the secondary, it's a lower activation energy and a more stable intermediate before we go to our final products here. So Markovna rule states that the hydrogen is going to go on the least substituted carbon, and the reason it's going on the least substituted carbon is the intermediate forms the more stable carbocation. Okay, so there's also some stereochemistry associated with this hydrohalogenation. Occasionally, you can form this by having a multi-substituted alkene, and because you get a mixture of Syn addition and anti addition, that means we're going to end up with a racemic mixture, okay? And the whole reason it forms a racemic mixture is our intermediate is this carbocation, which is trigonal planar. Now, the incoming halide can come in from the top, forming one isomer. In this case, it would form the S-halobutane. And if it comes in from the bottom, it'll form the other isomer, which in this case would be the R-halobutane. So because we're going through that carbocatalytic intermediate, just like before when we did reactions on it where we got carbocations would scramble our mixture, whenever we have that same thing happen during these hydrohalogenation reactions, we have a scrambling of stereochemistry in the final product.